Good evening, everyone. So I'll be presenting my work on automated verification of concurrent programs. As we just mentioned, my specific research area is verifying programs for weak memory models. But in this talk, I'm not going to talk about weak memory models at all. Another thing is, since this is mainly compiler community, this talk will be a little bit more theoretical than probably what has been presented so far. So, yeah, with that, first of all, the question is, why are we even interested in verification? Why do we want to do that? So this is a real world example of a bug that caused some deaths. What happened is there was a race condition which triggered more amount of radiation than should have been released, and that resulted in death of at least 6 people. So the thing is, depending upon how critical your piece of code is, you might want to have a proof of correctness rather than just testing it and saying it's most likely correct. So one of the logic systems that actually gives us proof of correctness is hold logic. I am just giving a very brief example of hold logic in case somebody has forgotten it. So the idea is we have something that we want to prove, which is the post condition of this entire program. There are some proof rules which manipulate these conditions. These is assert statement. So and after all of this manipulation, what we want is that our precondition, which is the assumption of the program, implies whatever we want to prove. So this is actually proving the correctness of a program mathematically. So this entire thing, it proves that after this execution of program, given value of x is 0 and value of y is 1, what we get is, value of x and y are 0 initially, this program will definitely give us this program state where x is 1 and r1 is 0. So this is mathematical proof, this is not testing. Then the thing is, hold logic works only for single threaded programs. So what do we do when we are going for concurrent programs? First question is, what are the challenges in concurrent programs? So normally when we have a single thread, we look at its execution and we know what the result is. But when we have more than one thread, we also have to look at the possible interleavings, which means in this case, we can get 3 different values of variables a and b depending upon how they interleave. So if we want to verify, or if we want to verify this program for all possible values of variables, then we have to look at least these 3 interleavings. In most cases, it may not be possible for us to find that, okay, these 3 interleavings are sufficient. I don't know, depending upon the technique that you use, you might be verifying more than 3 interleavings. Requirement here. Then the hold logic is used for, so one of the extensions of hold logic for concurrent program is relay guarantee reasoning. The idea is following: when we analyze one thread, we forget there are other threads. So when we are analyzing one thread, there is this one thread and something called environment. And whatever this thread can change will be considered guarantees of this thread, which is, okay, this thread can change program states according to these transitions. Now, these transitions become environment action for other threads. So the other thread, T1, doesn't know T2 exist. It simply knows that these environment actions are possible at any point of time during T1's execution. So when we are analyzing T1, we consider all of the changes possible in our preconditions, post conditions, or if you are calling them program states, so then program states based on these environment actions. So here I'll give an example of this relay guarantee reasoning, but because I wanted to go to an operational route rather than giving a logic-based proof, I'll be doing it in thread modular way rather than classic relay guarantee way. So what we have here is our precondition is x equals to 0 and y equals to 0. Now, if we look at these environment action, this first environment action can actually change this program state into x equals to 2 and y equals to 0. Which means the program state x equals to 0 and y equals to 0 is not stable. It's not inclusive of all possible program states that are possible here. So to make it stable, we need to make sure all possible environment actions are accounted for in these program states. So the program state here becomes x equals to 2 and y equals to 0 is also possible. Then This enables the second environment action, which should also be included. So what we get is this x equals to 2 and y equals to 1 is also possible. Further, when we have this instruction A executed, which is x equals to 1, then value of variable x will be changed accordingly, and we have these particular program state here where value of x is changed to 1. Again, we need to check with corresponding environment actions. So first environment action gives us something new, and then second environment actions gives us something new again. So this is the complete program state at this point. This essentially is like considering interleaving of this instruction at this point, if you look at it intuitively. And finally, we do the same thing with our final post condition, and this should also be stable with all of the environment action. So this is the idea of classic relay guarantee reasoning. Now we ask this question, do we need to look at all possible interleavings? Or in case of relay guarantee, we ask, do we need to look at all possible environment actions at all possible program points? So to answer that question, we look at this program again. If all we are interested in is the value of variable r1, suppose there is some certain variable r1, then we don't care what are the values of x at these points, which means we don't need to look at the interleaving of instruction C at any point in thread 1. Similarly, value of y is not important before A and after B. It's important before B, but not after B or before A. So we need to look at only one interleaving, which is when D interleaves before B. So in this scenario, we are basically saying we don't need to look at all possible environment actions. Why don't we look at a minimal set of them? So to do that, we came up with this idea of dependency-based relay guarantee reasoning, or DEP-RG. The idea of DEP-RG is, first of all, relay guarantee reasoning said relies and guarantee the environment action that we were computing. Those are for a single thread, for a particular thread. Here I am going to say these are per instructions, because I am interested in interleaving with particular instructions, not all possible interleavings here. So, and second idea is we will look at the interleaving of D before B only if by looking at that interleaving, we may get a new program state that we would not reach otherwise. So the keyword here is may. If at all it is possible to get a new program state, we have to look at it. Right. So the first thing we did to achieve this is we came up with this dependence relation. It's a little bit different than classic dependence relation definitions that were used in literature. Idea is this: let's say program state before B is y equals to 0. Then after executing B, we get R1 equals 0 here. Y equals to 0 and R1 equals 0. Now, if we execute D before B at this point, the value of R1 is different. So what we are seeing is, if by executing instruction D before B at a particular program state leads to new values of variables defined in B, then B is dependent on D in that particular program state. Now note that here B is dependent on D in y equals to 0, but in y equals to 1 it will not be dependent. So what this gives us is, when B is dependent on D in y equals to 0, we will say that whatever guarantees D is giving should be considered as environment action for B or relay for B. Otherwise, there is no need. So next we come to the definition of stability. How do we make sure we are looking at all possible program state we need to look at? So again, we look at this particular part of the program. If precondition here is y equals to 0, and this particular transition y equals to m goes to y equals to 1 is a relay is one of the relay actions for instruction B, then y equals to, then after taking this action, we can possibly reach y equals to 1, which means this program state is not inclusive, or it's not stable under this environment action. So to make it stable, we need to change it to y equals to 0 or y equals to 1. Now, even if this environment action takes place at this point, our program state will not change. So that's the idea of stability condition that we have defined. Now, this is a simple example, the same example that we had earlier, only thread 1 I am showing here. So if we are using classic RG, we will be getting all of these program states. But if we are using only if we are using the dependence based rely guarantee reasoning that I am proposing, then we are getting the program state that are green, only those ones, not the rest, not the others. So you can see here that it makes proofs much simpler, and program states are also less complex. Further, what we suggested is that the way we have designed our DAP-RG proof rules, they allow us to use abstract domains to represent preconditions or postconditions, which means the actual proof that we will get using DAP-RG for that thread, if we are using interval abstract domain, which simply says value of x is between 0 and 0 and value of y is between 0 and 0, then we get something of this sort. So if we use abstract domains here, the another thing we get is we can define transfer functions for these different instructions, and those transfer functions can manipulate these invariants very nicely. So one of the problems of whole logic was that we need to come up with these invariants. The same problem was also there in classic rely guarantee reasoning. By combining this with abstract interpretation, what we say is we don't need to come up with program invariants now. We can use transfer functions and other things that abstract interpretation framework gives us to come up with program state given some initial assumption. So our soundness, if you look here, our soundness theorem it's actually parameterized in two things. One is sigma and second is D. Sigma is set of program states, which I just said can be any abstract domain. And D is a set of dependence relation, which I have already given you a definition of dependence relation, but computing that particular dependence relation is quite difficult. It's inefficient. So anything that over approximate that dependence relation will work here. To compare classic RG with DAP RG, so first of all, classic RG uses predicate logic, and I am saying we will allow any abstract domain here, which means easier invariant generation, easier to automate the proof checking or verification process. Our states are simpler because of dependence relation, and since we are not looking at all possible interleavings, and that also results in much simpler proofs. In future, so currently we are actually working on both of these. I am implementing this technique, and implementation is almost finished. I am actually doing benchmarking. The second part is extending this particular technique for weak memory models. The idea for weak memory models is already there. So as I said earlier, we can use transfer functions for particular instruction to manipulate the program states. If those transfer functions are designed for a particular weak memory model, this technique can be used for that memory model. So the theoretical framework for weak memory model is also ready, and we have instantiated it for RC11 memory model and RA memory model already. Implementation work is pending over there. So that's it from me. Any questions?
Thank you, Divyanjali. Questions?
Yeah. So in your analysis of concurrent multi-threaded programs, do you assume the presence of locks or lock-free instructions?
As long as we can define transfer functions for locks, we can analyze locks. So I already have the definition of locks. The program with locks will work for us. There is no issue with that.
And what about lock-free functions which invoke compare and exchange operation internally?
I have also defined the transfer function for compare and swap or RMW operations, so that also works. Either is fine. And even if there is something that I have not defined, all you need to do is define transfer function according to the semantics, and it's done. But yeah, locks and compare and swap, they are both already handled.
Thank you.
Hello, nice talk. I just want to ask how whole logic is different from TLA plus, which is also quite in usage for writing formal spec for concurrent programs.
So whole logic is different from what?
TLA plus.
TLA plus.
Yeah.
So whole logic is a proof framework.
Right. TLA plus does also something similar, right? You define the spec and you define your invariants. and there is a proof system which proves that those invariants hold even temporally or whatever, uh, with all the cases, even if some let's say threads drops and everything.
So I am not familiar with TLA plus,
Okay.
frankly, but I'm sure somebody in our audience will know the answer.
No, it doesn't generate code, but it no, this in this also you define your spec, right?
No, whole logic is used to prove the correctness. You don't define the spec. You already have the spec.
Uh, okay, so they are working with program. So you have program and you can map it to this and can formally verify, is it?
We have a program, we
Yeah.
have a specification. We want to prove that program works according to the specification.
Okay, okay, okay. Makes sense. Thanks.